So welcome to Math 150, Section 2, Multivariable Calculus 2021. As I was telling the students who were here, this is going to be different than all the other lectures this semester because I am deliberately not going to do the same stuff in Section 1 and Section 2. I'm going to do different examples. So if you want to see more examples of worked out problems on Lagrange multipliers, watch the Section 1 video. You can watch it at 1.5 speed as well and just try to get a sense of how would you do the algebra. That is the worst part of these problems. The calculus, for the most part, is straightforward. The challenge is getting the algebra to work out. And a lot of times, the way we get the algebra to work out is we break things up into different cases. When you break things up into cases, it's okay if there's some overlap between the cases. It's not okay if you miss those. So how many people in here are a first-year student? How many people here are a second-year student? Okay, so if I just said, let's break the class into first years, would that cover everybody? No. What if I broke it up into first years and undergraduates? Would that cover everybody in this classroom? So everybody in this classroom is either a first year or an undergraduate. Thank you. Okay, who's not a first year or an undergraduate? Okay, yes, it's okay. Hi, guy with chalk, right? So if you broke it up into first years and undergraduates, there's an overlap between the two groups. Every first year is an undergraduate. Not everyone in this class is a first year. And in fact, not everybody in this class is an undergraduate. If you broke it up into first years, undergraduates, and people who have an undergraduate degree, then you would cover everybody in this class. You've got to be careful when you break things up into cases to make sure you get everything. It's okay if there are some elements involved, but you have to make sure you get everything. Frequently, when we do Lagrange multipliers, we have this helping variable lambda. At the end of the day, we don't care about it. So Lagrange multipliers and the goal is constrained mass or min. And so we have some constraint function. Maybe it's g x1 xn equals 0. Sometimes instead of 0, sometimes we say it equals c, or we might give a specific value. Doesn't really matter. This is the constraint. You can view it as a level set. And then we want to maximize or minimize the function f of x1 through xn. And what Lagrange multipliers tells us is the gradient of f at some point A is equal to lambda gradient of g at that point A, and g of A equals 0. That's what's true at a candidate for a maximum and minimum. It would be wonderful if our method gave us the points that the function took on its largest and smallest values. The quadratic formula is wonderful like that. If you're trying to find the roots of a polynomial of degree 2, and you know the coefficients, it's ax squared plus bx plus c, you just plug in a, b, c to the quadratic formula, and boom, here are your two solutions. Lagrange multipliers will not give you that. It will give you not even the candidates. It will give you a set of equations that the candidates satisfy. So from these, you can then deduce the candidates. If I have more equations than unknowns, do you think this should be a solution? So I have more equations than unknowns. So if I have more equations than unknowns, maybe 2x plus 1 equals 7, 3x minus 4 equals 21. Do you think this should be a solution? More equations than more unknowns. This should not be a solution in general. This first equation is enough to specify what x is. And it's very unlikely that that happens to be the same one as this. So if I give you more equations than unknowns, I don't expect there to be a solution. There might be. If I give you 2x plus 1 equals 7, and x equals 3, well, there is a solution. 3 works for both of them. So it's possible, but as a rule of thumb, if I have more equations than unknowns, I don't expect a solution. What if I have fewer equations than unknowns? 2x plus y equals 8. Do you expect that to have solutions? Yeah. Do you expect it to have finitely many or infinitely many solutions? For any value of y, I've got a value for x. Any value of x, I have a value of y. So if I have fewer equations than unknowns, I expect to have an infinitude of solutions. So the perfect balancing act is when I have as many equations as unknowns. If I have as many equations as unknowns, maybe I should only have finitely many solutions. So the hope is that the Lagrange multipliers will give you finitely many solutions. So when you're trying to do the math, it's always nice to have a sense of what the answer should be. So we would have df dx1 at a equals lambda df, I'm sorry, dg dx1 at a plus a dot df dxn at a equals lambda dg dxn at a and g of a1 an equals 0. How many equations do we have here? What's the number of equations?
N+1.
We have n plus 1 equations. And what's the number of variables?
N+1.
N plus 1. So we have a1 through an and lambda. So we do have n plus 1 variables. At the end of the day, we don't care about lambda. We only care about the point a1 through an. We only care about the coordinates. It might be easiest to find that point by first calculating lambda. But we only care about finding the point. Sometimes we often use x1 through xn and not a1 through an to the point. I was just doing this to emphasize, here we're taking the derivative and here we're evaluating it at the point. Often we just say, look, let's just take the derivative and we'll evaluate it at that point, and then we'll find the value of x1, xn that maximizes, minimizes. That solves the equation. And we've talked many times about why this works. So if this is the gradient of g, and the gradient of f is not aligned with the gradient of g, then I have some component of it that's tangent to the curve. And that means if I flow in that direction, I can make the function larger, and if I flow in the opposite direction, I can make it smaller. And then if over here, if this is the gradient of g, and the gradient of f is in the same direction, then that will be my candidate for maximum minimum. So again, Lagrange multipliers doesn't give you a guaranteed maximum or minimum, it gives you a candidate. For a lot of problems, it's clear if you're going to get a maximum or minimum. If you're trying to find the point on a curve that's closest to a fixed point. Yes?
Isn't your curve f?
No. No, my curve is your g of x1 through xn equals 0. That's my constraint. And the gradient of g is the normal to the curve. And then I'm trying to maximize the function f. And so at each point on the surface, I can see how is my function f changing.
So wouldn't, sorry.
Yep, no.
So wouldn't the gradient of g be tangent if it's g?
No, this is the surface, g equals 0. So the gradient of g is the normal to the surface. If you think of the sphere, x squared plus y squared plus z squared equals 1, the gradient of g is just x, y, z. So at a point it's in the same direction as the radius, it's perpendicular to the sphere. So the gradient of g is going to be normal to the surface, g is constant. If you want to think of it as you have your different level steps, here might be g equals 1, here might be g equals 2. And the gradient is telling you what direction to go to see g increasing as fast as possible. You're going from one level set to another. perpendicular to that, you'll see no change. You're staying on the level side. So if you have a surface with g of x equals 0, the gradient of g is the normal. And I want my gradient of f to be in the same direction as the gradient of g. If it's not in the same direction, it can't be a candidate to maximize or minimize that. Yep. Now, it is possible that the gradient of f could be 0. If the gradient of f is 0, then what must be true about lambda? So if the gradient of f is 0, all of these on the left-hand side are 0. So what should be true about lambda?
It's 0.
It's 0, or the gradient of g happens to be 0 as well. So normally we will assume we have a surface where the gradient of g is not 0. That it does have a non-zero normal at every point. It is possible that the gradient of f could vanish on the surface. And that's also a candidate. So it is possible that lambda could be 0. When you divide equations by equations, the danger is always have we divided by zeros, the denominator is 0. And it is possible that lambda could be 0. We have to be careful. We need to break things off into cases. Case 1, lambda is 0. Well, frequently if lambda is 0, then it's very easy to analyze. Case 2, lambda is not 0. So always you'll be careful if you ever do any division that you haven't divided by 0. We do have enough equations and enough unknowns that it's perfectly balanced and that there is a chance that everything will work. So the other thing is, who is our favorite New England transcendentalist writer? Thoreau, patron saint of mathematical advice. And what advice does Thoreau give us? Simplify, simplify. So important, he emphasizes it. Before you spend a lot of your time doing algebra, it is worthwhile to spend a few minutes and say, is there a way I can rewrite this to make the algebra a little bit better? So sometimes, as I was mentioning, for some problems, you can tell, I know I'm going to have a maximum or I know I'm going to have a minimum. If I have a fixed point and I have some curve going off to infinity, and I want to find what point on the curve is closest to this point, it's not going to give me the maximum distance, because the maximum distance is going to go off to infinity. So whatever candidates I get will have to be candidates for the closest point on the curve to the point. If I have a fixed perimeter and I'm trying to maximize area, I know I'm going to get a maximum area, not a minimum area when I'm doing things, because I can make the area go all the way down to 0. So sometimes you have some intuition as to what kind of value you're going to get. Now, I mentioned distance before. Distance is a terrible function to work with. Why is it painful to look at the distance between 2 points? It has a square root. Thou shalt never minimize distance. What should you minimize? Distance squared, right? If you minimize the distance squared, is it effectively the same as minimizing the distance? No. What is the area of a triangle? Give me a formula for area of a triangle. Most common, you family feud. Yep. We asked 100 mathematicians, give me a formula for the area of a triangle. Top 2 answers on the board. What's the top answer? 1/2 base times height. So if I want to maximize the area of a triangle, I could work with 1/2 base times height. Or I could say, screw that, I'm going to maximize the doubled area. Now, if I maximize the doubled area, I just don't have that factor of 1/2 floating around. So I can just make the algebra a little bit nicer. How many of you have ever heard of Hero or Heron's formula for the area of a triangle? Yes. So 2s is equal to x plus y plus z. So I give you a triangle with sides x, y, and z, and it turns out that there is a formula for the area. So the area, as a function of x, y, and z, is the square root of the semi-perimeter minus x, semi-perimeter minus y, semi-perimeter minus z. And I could ask, given a fixed semi-perimeter, what triangle has the largest area? What do you think the answer is going to be?
What's the semi-perimeter?
So the semi-perimeter is half the perimeter.
Oh,
So S equals semi-perimeter equals 1/2 times the perimeter. And just when you look at the semi-perimeter, it's just a cleaner formula to use. We don't want to maximize the area of a triangle. What do we want to maximize? The area squared, right? This involves a square root. So instead of trying to find which triangle has the largest area, let's find which triangle has the largest area squared for a given perimeter. So that will make the algebra a lot nicer. We're still going to have to differentiate a product, but I would much rather differentiate a product than the square root of a product. The next simplification I can ask is, what can you assume is the semi-perimeter equal to? Without loss of generality, what is the semi-perimeter equal to? I claim that there's a natural number that you can associate and say, rather than considering an arbitrary value of S, it's enough to study one specific value of S. Without loss of generality, you can assume S equals 1. Imagine the semi-perimeter equal to 8. I could change units and rescale everything by a factor of 8. Is it going to change the geometry of the best triangle? What if the perimeter of the triangle was 3? Could I just divide x, y, and z by 3? Instead of measuring things in feet, I'm measuring things in yards. Or if I have 100 for the perimeter, I could divide everything by 100 and measure things in meters rather than centimeters. So without loss of generality, if you want, you can assume S equals 1. So without loss of generality, you might as well assume S equals 1. There's just one less quantity to be floating around. If somebody then gives you, I'm not going to give you 1 meter of fencing, I'm going to give you 40 meters of fencing, well then just multiply everything by 40. And it just makes things a little bit cleaner. The only thing you can't rescale it to is 0. Well, if I have 0 meters of fencing, do I expect to be able to construct a triangle with maximum area? I have no fencing. So I can only do this if I have some positive value for S. I might as well assume S equals 1. So what's my constraint? What's the constraint going to be? X plus y plus z equals 2. So I can write as g of x, y, z, x plus y plus z equals 2. I could have also written it as x plus y plus z minus 2 equals 0. I could have done it that way. It doesn't matter. You can either have g of the variables equals 0 or it equals some constant. Doesn't matter. Either way is fine. What is my function that I want to maximize and minimize? I want to maximize f of x, y, z is 1. What do I want to maximize? So what would the area squared be? So what is it? But what is S? 1. So now it just becomes 1 minus x, 1 minus y, 1 minus z. That's a lot better. And now we can start calculating gradients. So the gradient of g is dg dx, dg dy, dg dz, 1, 1, 1. Right? The gradient of g is not that bad to compute. What about the gradient of f? So it's df dx, df dy, df dz. So I'm going to take the derivative of this with respect to x. What do I get? So what would be the derivative of this with respect to x? I'm sorry? Sorry? Minus 1 is the start of it, but minus 1 times what? Times 1 minus y times 1 minus z. I've got a product. If I'm taking the partial with respect to x, 1 minus y, 1 minus z, these are constants. So it's just the derivative of 1 minus x with respect to x. It's just negative 1. So it's just going to be negative 1 minus y, 1 minus z. What's the derivative of f with respect to y? Negative 1 minus x times 1 minus z. And the last is negative 1 minus x, 1 minus y. You can see that there's a lot of symmetry in this problem. Is that the roles of x, y, and z are symmetric. So if I take the derivative with respect to x, I should be able to immediately figure out the other ones, or you can just do the calculation. So I will try to leave this on the board as long as I can. Now we just have to do the algebra. So we want to solve. And so we have gradient of f is lambda gradient of 2. So what does that mean? So we have the gradient of 2 is just 1, 1, 1. As we have negative 1 minus y, 1 minus z equals lambda. Negative 1 minus x, 1 minus z equals lambda. Negative 1 minus x, 1 minus y equals lambda. And then our constraint, x plus y plus z equals 2. I'm trying to make the two distinguishable. When you look at this, any thoughts about how to solve this? So now we have to do algebra. The amount of calculus is minuscule. Once we take the partial derivatives, we're done with calculus. The rest of the problem is just doing algebra. So when you see this, does anything scream out to you? Yes? Okay, so we subtract one equation from the other. Since they all equal lambda, they must equal each other. We can also drop the negative signs if we want. And so we can get 1 minus y times 1 minus z equals 1 minus x times 1 minus z equals 1 minus x times 1 minus y. What would you like to assume now or deduce? So what would you like to do now? This wonderful start. So we need to solve it. When you look at this, 1 minus y times 1 minus z equals 1 minus x times 1 minus z. Let's just focus on that. 1 minus y, 1 minus z is 1 minus x times 1 minus z. What does that suggest? Yeah, it suggests that 1 minus y equals 1 minus x. And if 1 minus y equals 1 minus x, y equals x. Can you do that?
Wait, which one is it? Z doesn't equal 0?
So we now have two cases. Case 1, z does not equal 1. So if z does not equal 1, then you get x equals y. Or to do it a little bit more detailed, you would get 1 minus y equals 1 minus x. Therefore, x equals y. Yes?
Could you already assume? Oh, never mind.
Yeah. And so now that we have x equals y, we can look at the last equation. 1 minus x, 1 minus z equals 1 minus x, 1 minus y. 1 minus x, 1 minus z equals 1 minus x, 1 minus y. We know x equals y. What would you like to assume now? What would you like to deduce?
That z is equal to 1.
We'd like to deduce that z equals y equals x. Can we cancel the 1 minus x from both sides?
X doesn't equal 1.
So now we have subcase 1, x does not equal 1. So we're in case 1, z is not 1. And now we're in subcase 1 when x doesn't equal 1. If that's the case, then we get 1 minus z equals 1 minus y, therefore z equals y equals x. Okay. What's the other case we have to do? What subcase we have to do?
Okay, I'm still going to ask it. Could we assume that z is not equal to 1 or x is not equal to 1 because then you wouldn't have a triangle with perimeters?
Well, you could have a degenerate triangle. You could say initially that x, y, and z all have to be positive. And if one of them is equal to 1, then the only way that happens is you would have to have a degenerate triangle. So if you make some argument at the beginning that none of them can be 1, because if x is 1, the sum of the three sides has to be equal to 2. The only way that can happen is if z and y are both adding up precisely to x, and you have a degenerate triangle like this. You have no way to come up. To do it very carefully and methodically, you would now have, subcase 2, x equals 1. Well, if x equals 1, what do we know about the area? It's 0. Is that going to be a maximum? No. In fact, that will be the minimum. So it is possible to have x equals 1 or y equals 1 or z equals 1, but those will all give 0 area. And so that's very similar to the remark that you were making. We don't really have to consider all of these dangerous cases because they will all give us 0 area. But this is the careful way to do it, to break it up slowly into cases and subcases so you don't miss anything. Case 1, z does not equal 1. And then as I'm analyzing it, I get to this point and I said, I would love it if x was not 1, because then I could cancel the 1 minus x's, so that I have a subcase when x is not 1. And then I have to handle the case when x equals 1. And that completes the analysis when z does not equal 1. Now what do I need to study? We've done the case when z is not 1, when z is 1. So then we would have case 2, z equals 1, and the area is just 0 in that case. So we know x equals y equals z, and we have an equal out of time. And that would be how to solve the problem. Any questions about this? There is another way you could have tried to do the problem. You could have tried to replace z with maybe 2 minus x minus y and try to just reduce the variables by 1. You can try that. It's going to make it for a more painful problem. Okay. So any questions about this? This is a really good example of how to do Lagrange multipliers. It breaks things up into lots of different cases. You see that the amount of calculus is almost nothing. You just take partial derivatives and that's it. And then it's trying to find the best way to handle the algebra. So the problem we did in the first class was looking at a right triangle and trying to figure out which right triangle of a given perimeter has the largest area. Anybody want to make a guess as to what kind of right triangle it would be? So what right triangle for a given perimeter do you think would be best? Can't be. Because it's a right triangle.
Oh, right, right.
Yeah. So of the right triangles, which right triangle do you think will have the greatest area?
Like,
So what is that? What kind of right triangle is that called? So it's 45, 45, 90, but that right triangle has a special name. Isosceles right. So the isosceles right triangle, my intuition is that would be the best right triangle for given group. And so we went through and the algebra became quite painful. But if you look at it the right way, if you keep trying nice thing, it's not so bad, and you do get at the end of the day x equals y, and you do get it an isosceles right triangle. Okay. So I thought we would do just one more standard example, and then just one where the algebra isn't so bad. But as a rule of thumb, I would much rather do many easy problems than one hard problem. And so here, I keep breaking things up into cases and subcases, because as I do that, I get to assume more. When you don't break it up into cases, you have complete freedom in what everything is. But if you say, I'm going to assume z equals 1, now you get to use that. Or you can say, I'm going to assume z is not equal to 1, and now you can use that. And so once we assume that z was not equal to 1, we could divide by 1 minus z. All right, so let me just pull a problem at random. So we have the constraint is g of x, y, and hopefully this is not one of your homework problems. 4x squared plus 9y squared equals 36, and f of xy equals x times y. Right, there's a nice interpretation of this. So we want to solve this problem. What kind of curve is 4x squared plus 9y squared equals 36? It's an ellipse. If I divide both sides by 36, it's the same as x over 3 squared plus y over 2 squared equals 1. So I just divide both sides by 36. That's x squared over 9, which is x over 3 squared. So this is an ellipse. If I draw the ellipse, this is the point 3, 0. This is the point 0, 2. Now I take some point and I want to maximize x times y. So one way to where x and y is on the ellipse. Without loss of generality, can I assume x and y is in the top right quadrant? I'm really maximizing that area. Well, another way of looking at that is the same as maximizing that. So it's basically saying, what's the largest rectangle I can put in by just taking one point and looking at its reflection? X, y, x negative y, negative x, negative y, negative x positive y. So there's a nice geometric interpretation to this problem. We don't need to do that, we can just do this formally. So I need to do gradient of f is lambda gradient of g, and g of xy equals 36. So what's the gradient of g going to be? So dg dx, dg dy, what would that be? So what's the gradient of g? I first take the derivative with respect to x. What's the derivative of 4x squared plus 9y squared with respect to x? 8x. And what's the derivative of somebody else with respect to y? 18y. And now if I do gradient of x, that's df dx, df dy. What's the derivative with respect to x? Y, and then with respect to y, it's the x. So now we get y equals lambda times 8x. We get x equals lambda times 18y. And we get 4x squared plus 9y squared. So this is the first one where the algebra looks a little bit more interesting. So now we need to figure out how to solve it. So when you look at this, it should yell at you to do something. When you look at those three equations, two of the equations are yelling at you, please, please do this to me. You could substitute. I think it's something that's a little bit nicer. It's similar to substitute. Yeah, which ones would you want to divide? Yeah, if we divide 1 by 2, we get rid of lambda. And we drop an entire variable. And then we'll have two equations and two unknowns rather than three equations, three unknowns. You could also substitute. But I think it's cleaner to divide and get rid of the lambda. Do you have to worry about dividing? Okay, so if lambda is 0, then what's true about x? And then what would be true about y? So if lambda is 0, then x is 0 and y is 0. And we know the point 0, 0 is not on either. Okay, but when we're dividing, what if y is 0? Well, if y is 0, then x is 0. And we would then get the point 0, 0 again. And if x is 0. So case 1, x, y, or lambda is 0. We get x equals y equals 0, not on a list. So we don't have to worry about that case. So case 1 is if anything in sight is 0. If x, y, or lambda is 0, and we've just shown we don't have to worry about that. So case 2, x, y, and lambda are not 0. Now when we divide, we get y over x is 8x over 18y. Well, we can simplify 8x over 18y a little bit. That's just going to be 4x over 9y. Any thoughts when you have y over x equals 4x over 9y? So y over x equals 4x over 9y. What can we do? Yeah, we could just cross multiply, get rid of the fraction. So cross multiply. And now you'll get 9y squared is 4x. We could solve for y in terms of x, right? So we get 3y equals plus or minus 2x. So y is going to be plus or minus 2/3. And so if we're assuming x and y in the upper right quadrant, then we would get your y equals 2/3. Unfortunately, we don't know the value of x or y. How could we find the value of x or y? Yeah, we have 3 equations and 3 unknowns. So now, use the constraint. We have 4x squared plus 9y squared equals 36. Do I want to write y equals 2/3 x? No, what do I want to do? I could substitute in y equals 2/3 x squared and multiply by 9. What's the fast way to do the algebra? Yeah, we know 9y squared is 4x squared, so why not use that over here? So again, look at the algebra. You'll get the same answer, but you can simplify it in a few steps. You now get 4x squared plus 4x squared is 36. So we get ax squared is 36. So x squared is 9/2. So x is plus or minus 3 divided by 3 is 2, or plus or minus 3 root 2 over 2. We're done. We know it's going to be the plus root because we're looking to maximize in the first quadrant. But this is how you would do the algebra. And now that we know x, we could of course solve for y by just taking 2/3 of that. And in fact, you can see that it's nice to write it as 3 root 2 over 2, because now when I take 2/3, what do I get for y? I get y equals the square root. Okay. So any questions about this problem? So this is your prototypical problem where the algebra works out nicely. And you can really follow your nose in terms of how to do this. I've got my 3 equations. I take the partial derivatives. I put them, grad f is lambda grad g, and I keep my constraint. And I see, oh, I've got these things like lambda here. If I take a ratio, the lambda goes away. I just have to justify that I can take the ratio. That's my case 1 and case 2. And now I just have to do the algebra. And the key idea there was to cross multiply. So in the section 1 video, the very beginning of that class is the same as this, with the formation of Lagrange multipliers. Then they have the right triangle example, and then they end with the triangle inscribed in a circle. I'll do that one over here because that's a really nice problem. And one of the hardest points in math is trying to figure out a good way to attack a problem. And this is why, as much as I can, I want to try to do some lectures to just try to guide you. So imagine I have a circle. What's the radius of my circle? Without loss of generality? 1. And I want to choose the triangle that has the greatest area that's inscribed. Or maybe the greatest double area. 3 points, circle of radius 1. Maximize double area. So there's a lot of freedom. I get to choose any 3 points on the circle. Without loss of generality, what can I assume about one of my 3 points? Where is one of my 3 points without loss of generality? 0, 1. So you have elected to essentially put on the North Pole. That's one of the 2 natural places to put it. Where's the other place people would put it? 1, 0, right? Doesn't matter which one you do. So by doing that, I said, well, let me just rotate the damn circle and put one of the points at the North Pole. And now, how many points do I have to play with? 2. Isn't that a lot better? Instead of having 3 points to play, that's 2 points. That's the advantage of doing the Thoreau first, is trying to simplify. I would much rather, instead of having 3 points to place, I'd much rather have 2 points. Yeah. What's even better than just having 2 points to place? 1. I'm going to show you how to do it by placing just 1 point. When I give you any triangle, if I take these 2 points here, do you agree that there's a unique point that's halfway between them on the arc? Where should I put that point? Where should I put the point that's halfway between them? You just told me if I had one special point, put either at the North Pole or at 1, 0. Where should I point this special point? It's the same thing, right? I have one special point now. Where should I put that special point? Either the North Pole or 1, 0. So if I give you any triangle, I can take one of the sides. And what I'm really doing here, I'm splitting it up like that. So if I draw it now like this, here's my center. I go up theta, and I go down theta, and I go down theta, and here's one side. This is one side of the triangle. And I'm just using the point 1, 0 as right in the middle. I now have to choose where to put my third point. But I want to maximize the area. What's the area of the triangle? 1/2 base times height. So the area of a doubled area is just base times height. Here's my base. Where's the height going to be maximized? At what point? What's the coordinate where the height is going to be maximized? Negative 1, 0. So the maximum height would be if I put it over here. If I put it over here, then my height is only this much. If I put it here, my height is this much. If I put it here, my height is larger. I could, of course, also put this all the way over here, between the 2 points. So technically, you have to worry about both of those, but it should be clear that if I'm going like this, I want to be on the opposite side of the center of these 2 points. Okay? And if the center happens to be right in between the two, then it doesn't matter. So I want to be at negative 1, 0. So this is going to be my triangle. Notice now, I only have one free parameter, theta. I no longer have Lagrange multiplier. I just have a function of theta. This is 1, this is 1, this is 1 because they're all radii. If this is theta, what's this length over here? Right, or so just this part over here would just be sine theta. And this part here would just be cosine theta. So what I can do is I can have my function f of theta is going to be 1/2 base times height. So it would be 1/2 1 plus cosine theta times 2 sine theta. So it would just become sine theta times 1 plus cosine theta, or sine theta plus sine theta cosine theta. How do I find where this is logical? You've got a function of one variable. How do you find where this function of one variable is logical? Take the derivative. And so we get f prime of theta, derivative of sine is going to be cosine. Now it's the product. The derivative of sine is cosine. We get cosine theta, cosine theta, cosine squared theta. And now we have the derivative of cosine theta, which is negative sign here, minus sine squared theta. And we want to set this equal to 0. Okay, so now we have to solve this equation. Does anybody know a relationship between sine squared and cosine squared? What's the relationship between sine squared and cosine squared? I'm sorry? This sum is 1. Excellent. So sine squared is the same as 1 minus cosine squared. Okay. We get cosine theta plus cosine squared theta minus a minus cosine squared theta is plus 2 cosine theta squared minus 1 equals 0. So we have to solve 2 cosine theta squared plus cosine theta minus 1 equals 0. How can we solve that? Anybody know how to solve it? So much of it is trying to look at this divisor. Does this remind you of anything? Well, how would you factor? So what can we replace cosine theta with? X. So if I write x equals cosine theta, this is 2x squared plus x minus 1 equals 0. Do you know how to solve this? If you know how to solve this, why didn't you know how to solve this? Because I wrote cosine theta rather than x. Depending on how you write the algebra, I can make it very painful for you. But this, so cosine theta equals x equals negative b plus or minus the square root of b squared minus 4ac is going to be plus, I'm sorry, negative b plus, oh sorry, b squared, which is 1, minus 4ac, which is plus 8, divided by 2a, which is 4. Clearly, the negative root is not going to work. And so we get negative 1 plus the square root of 9, negative 1 plus 3 over 4. That's 2 over 4 is 1/2. So what angle has a cosine of 1/2? Because it's the weight, 5/3 or 60 degrees. And if you think now, if this is 60, this is 60, this has to be 30, that has to be 30. If this is 60, this has to be 120. This has to be 120. Isosceles triangle. So the sum has to be 180. If this is 120, those must each be 30. And lo and behold, what kind of triangle do we have? We have an equilateral triangle. We did not have to use Lagrange multipliers. We were able to reduce it down to a one variable calculus problem. This is the power of flow. This is the power of really spending some time thinking about what you have. It is not easy to do this. This is really hard. But I want to try to show you a few problems like this. Okay? And so when the dust settles, everything is really nice. But take the time when you have a problem to see if you can simplify.